And Saburo is, although still scientifically young, is already very well known for modeling the internal structure of giant planets in the solar system and beyond. And he's going to tell you about that giant planet.
Thank you, Ravit. Um, yeah, so today I'm going to talk about the interior and evolution of giant planets. So it's a very broad title, and actually I will mostly talk about the planet that you see here on the video, which is Jupiter. But the way we study a planet like Jupiter could be applied to any giant planets. And so to understand what's inside Jupiter, what we do is that we make models that are constrained by the gravity field of the planet, which is measured by a space mission called Juno. And so the Juno spacecraft has been orbiting Jupiter since 2016 and will continue up to 2025. And by the way, it's thanks to a camera called the Juno Cam that we can get those spectacular images on which you can see very detailed features on the surface of the planet. So here is the outline of my presentation. So I will start with an introduction, and then we'll see how to model the internal structure of giant planets. Then in the third part, I will present some results of interior models of Jupiter that are based on the Juno data. And this is the work I've essentially been doing during my PhD. And in the fourth part, I will talk about another type of models, which are evolution models. And we'll talk about Jupiter, but also Saturn. And this is the work I've started to do since I joined Ravit's group. So to begin with, the four giant planets in our solar system represent more than 99% of all the mass of the solar system except the Sun. And Jupiter itself has a mass of more than 300 times the mass of the Earth. And if we look at the composition of Jupiter, we can see that it is essentially made of hydrogen and helium, and there's only a tiny fraction of other elements that we often refer to as heavy elements. And if we compare the composition of Jupiter to the Earth and the Sun, we can see that actually Jupiter is much more similar to the Sun. And this is one of the first reasons why we study a planet like Jupiter, because Jupiter and the other giant planets are made of this primordial gas, namely hydrogen and helium. And that's why we think that they highly influenced the formation of the solar system. About formation, the standard theory tells that giant planets form by first accreting solids and forming a core. And this is then followed by a simultaneous accretion of solids and gas. And finally, there's a rapid phase of gas accretion. And so it's very important to study the present day structure of Jupiter because it's the direct result of its formation and evolution. And these are some key questions that our community tries to bring answers to. What's the internal structure and composition of giant planets? Is there a core inside giant planets? How do giant planets evolve? And another reason why we study Jupiter and the other giant planets is that we have now discovered more than 5,000 exoplanets in our galaxy. So studying the closest giant planets to us is important in order to better understand those far other worlds of exoplanets. And this mass radius plot shows you that actually many exoplanets are giant exoplanets. So of course there's a bias because we now know that the first exoplanets to be discovered were the so-called hot Jupiters. And we now think that the most abundant planets, exoplanets in our galaxy lie in between the size of the Earth and Neptune. But still, those giant exoplanets are interesting because they are probably the first ones to form in the systems. So on the one hand, we have a bunch of exoplanets on which we can perform statistics. And on the other hand, we have the giant planets in our solar system on which we have very detailed information. And by detailed information, I mean information about the structure and composition of their atmospheres, but also we know about their gravity field, which is very important to infer the interior of those planets. And this detailed information has essentially been obtained thanks to space missions. And one of them, as I already mentioned, is the Juno mission. So the Juno spacecraft is on an elliptical polar orbit, which allows it to pass very close to Jupiter at actually less than 3,000 kilometers above the cloud deck. And thanks to that, we can get those very impressive pictures. So on the left, you see some clouds and winds and some dynamical processes that we observe at the surface of the planet. And on the right-hand side, you see the vortices that we observe at the poles of Jupiter. And so Juno is measuring, of course, many things, but what is interesting for us is that it is measuring the gravity field of the planet. And it is doing so by scrutinizing the tiny variations of the orbit of the spacecraft using Doppler tracking. So we can estimate the gravity pull from the planets on the spacecraft by looking at the radio signal that is Doppler shifted and that we receive from the spacecraft. So Jupiter is rotating very fast. Its rotation period is less than 10 hours. And so it's not perfectly spherical, but it's slightly flattened. And the departure from sphericity can be expressed in the gravity potential of the planet as an infinite sum of some coefficients, J's, that we call gravitational moments. And those gravitational moments are measured by the Juno mission. And you can see that they depend on the density distribution inside the planet. So those gravitational moments, those J's, are really a way to link observations with models. So typically what we do is that we make a model in which we assume a certain composition, we get the density distribution, and then we compute numerically those gravitational moments and compare them to the ones observed and measured with Juno. And what you have to understand is that the accuracy that we've reached with the Juno mission is really amazing. And I'll try to convince you with this figure. So this figure shows the gravitational moments of all the 4 and 6 that we often use to constrain the interior of the planet. And so the large purple error bar that you see here corresponds to the measurements we had on those J's after the flybys of Pioneer and Voyager in the late 70s. Then the gray error bar shows the accuracy we had after the Galileo mission in 1995. And so Galileo orbited Jupiter, but by the way, it also sent a probe which dove in the atmosphere of the planet, and this provided very valuable information. Then the red error bar is quite off and corresponds to flybys of Cassini and New Horizons. And finally, the small blue error bar shows you the accuracy that we have on those gravitational moments thanks to the 2 first orbits of Juno around Jupiter. And that's not all, because after a few other orbits, we could even increase the accuracy of those gravitational moments. And now you can't even see the error bar on this small yellow dot.
Question.
Yeah.
Do you have to use the Basel functions, or I mean, could there be more optimized parameters for this?
For the gravitational moments?
Like it's always using these J numbers, but would it be more optimal to use something else? Maybe given that the density profile, maybe is not following.
So here it's an expansion using Legendre polynomials. And what I don't know if Bessel functions could be used here, because it's a fluid planet, we assume symmetry. Yeah. So it's just the radial profiles and also the component on the colatitude parameter, but on the azimuthal component we assume symmetry. And so before we jump into how to make a model of the interior and what we can infer from the interior of Jupiter, I'd like to give you a glimpse of what's inside Jupiter. And I like to do that on a historical perspective. So when I write Jupiter's evolution in the last century, it's of course the evolution of our view of Jupiter in the last century, right? And actually, the first interior model of Jupiter was made exactly 100 years ago by Sir Harold Jeffreys. And at that time, he didn't have accurate measurements of the gravitational moments from a spacecraft, of course. But using a clever constraint that involves the moment of inertia, he could constrain the density of the outer region of the planet, and it had to be very low density. And it could only be hydrogen and helium. Then in the 70s, here is the picture we had on the interior of Jupiter. So again, it was before the flybys of the first space missions. But at that time, you could use the motions of the natural satellites to get those gravitational moments. And so here, Jupiter is made of a central core, purely rock and ices, that would represent perhaps 1% of the mass of the planet. And this core is surrounded by a massive envelope of hydrogen and helium. And you can see here a demarcation because at that time, it was already suggested that when you arrive to sufficient high pressure, the molecular hydrogen will transition to a form that we call metallic hydrogen. So the pressure gets so high, and probably around the megabar level, your molecular hydrogen is squeezed so much that it dissociates and ionizes, and that's why we are left with this metallic hydrogen. Then appeared the so-called three-layer models, which is not very different from the previous model, except that now we have a helium-poor outer region above a helium-rich inner region. And this is thanks to work by, in particular, Stevenson, who showed that a phase separation between hydrogen and helium should occur, and this would lead to helium concentrating, forming droplets that will sink towards the deep interior under the influence of gravity. And the picture today has added a bit more complexity because we have now added this fourth layer of a dilute core. So this dilute core, well, instead of having a sharp discontinuity between the core and the rest of the envelope, you now have something that is more gradual. So the heavy elements are gradually distributed from the center towards the outer part of the planet. And so, in fact, this dilute core idea was not new. It was already suggested in the 80s, but it's really the accuracy on those gravitational moments from Juno that allowed to confirm its presence inside Jupiter. So before Juno, we had this picture of the three-layer model with a sharp discontinuity between the core and the envelope. So here it's Z, the mass fraction of heavy elements. So it's just the distribution of those heavy elements. And now with the dilute core, we now have something that is more gradual, as you can see here. And so an important paper was the paper from Chaunois 2017. And it led to, of course, to new questions, such as what's the extent of this dilute core inside Jupiter? And there are still some tensions about this question because on the one hand, you have interior models that are based on the Juno data that suggest a quite extended dilute core, so probably up to 60 or 70% of the radius of the planet. While on the other hand, evolution models suggest that it should be more compact, so probably no more than 20 or 30% of the radius of the planet. Another issue is that all those interior models suggest that the abundance of heavy elements in the atmosphere or in the outer region of your models is very low, so probably subsolar or solar, but we know that the atmosphere of Jupiter is actually enriched by a factor of 3 compared to the solar value. And so to solve these issues, modelers came with new ideas, and one new idea was this possible inverted Z gradient, which is illustrated here in blue. So it's a bit counterintuitive, but you will start in the very outer region, in the atmosphere of the planet, with a significant enrichment of the atmosphere, and then you would have this inverted Z gradient in order to have a region of very low abundance of heavy elements. But I'll get back to that later in the presentation. So this was to give you the context of how we study Jupiter's interior and what are the current questions. And now I'd like to talk about how to model the internal structure of giant planets. So first of all, you need to solve the classical structure equations to make a model. So those equations are the same as for a star, except that you don't account for the nuclear reactions, of course. And then you can build a model. And here I'm showing you possible temperature pressure profiles of the 4 giant planets in our solar system. So of course, it depends on many things, such as the equation of state that you use, the heat transport mechanism that you assume in the interior. But the first constraints that we can use to help us build those models are atmospheric measurements. And for Jupiter, I told you about this Galileo mission, which sent a probe that dove in the atmosphere of the planet, and it measured the temperature profile of the planet in the very outer region. So of course, it was dropped in one single location of the planet, so the representativity of this measurement over the whole range of latitude and longitude is still a matter of debate. And in the deep interior of your planet, the temperature structure remains uncertain. So we traditionally assume that it was adiabatic, but now with this potential composition gradient due to this dilute core, it may not be adiabatic anymore. Then we also have information about the composition of those atmospheres. And this figure shows you the measured abundances of some species in the atmospheres of the 4 giant planets of our solar system. And what you can notice is that all those giant planets have an atmosphere that is enriched compared to the protosolar abundances. So the enrichment is probably by a factor of 3 overall for Jupiter, maybe 10 for Saturn. And actually, it's very challenging to find interior models that agree with such enriched atmospheres. Then the second type of constraints that we have, and I already mentioned them, are those joining again. Is it shared on the Zoom? No, right? Okay. Okay, sorry for that. So, so we have those gravitational moments that allow us to constrain the interior of the planet, and the contribution functions of those gravitational moments really peak at the outer region of the planet. So this means that those gravitational moments directly probe only the outer region of the planet, and the very deep interior of the planet has to be inferred indirectly from those models. Now, if we superimpose a phase diagram of hydrogen on top of these TP profiles, so we notice that, for instance, Jupiter is crossing this boundary between molecular hydrogen and metallic hydrogen. So that's why we expect this presence of metallic hydrogen in the deep interior of the planet. And in the very center of the planet, pressures can reach up to tens of megabar and temperatures up to several 10 to the 4 K. So these are really extreme conditions, especially compared to what we have on Earth. And at the location of this molecular to metallic transition, we expect a phase separation between hydrogen and helium. And with this will result in this helium rain that will enrich the inner region of the planet in helium. And so we need to a good understanding of this phase separation between hydrogen and helium in order to properly model the interior of Jupiter. And we also need a good understanding of the equation of state over the whole range of pressure temperature that is covered by the adibats of those planets. And so for that, we need the help of the high pressure physics community, which carry out experiments and also numerical calculations in order to understand the behavior of hydrogen and helium. And so we need it for both the equation of state and the phase separation. So on the one hand, you have experiments such as diamond anvil cells or shock experiments, which can reach up to a few megabars. But usually those experiments provide only a few data points. So far, we have mostly relied on those ab initio calculations, which model the behavior of hydrogen or mixture of hydrogen and helium at high pressures using relatively computationally expensive calculation. And here at the Institute, we have Guglielmo and Cesare, who are currently working on those calculations of hydrogen at high pressure. So the equation of state is really a key ingredient in those interior models. And you'll see that it is still an important source of uncertainty. So on this figure, I'm showing some density profiles of Jupiter for 5 different equations of states that are available on the market, let's say. And you can see that the variations between those equations of state can reach up to 10%. And it's clearly non-negligible given the accuracy that we have now reached on those gravitational moments. So we should really continue to investigate on this equation of state of hydrogen, but also helium. So to make an interior model, you first need some initial conditions that can be the mass or the rotation period of your planet. So it doesn't have to be Jupiter. It can work for any giant planets. Then you need this equation of states, and you also need some parameters of your model. And it can be the core mass, the surface temperature, and the composition. So here, X, Y, and Z are the mass fractions of hydrogen, helium, and heavy elements, respectively, in the different regions of your model. When you have all of that, then you can solve those hydrostatic equations and then compute the gravitational moments using a particular mathematical theory that can be the theory of figures or the concentric Maclaurin theory method. And once you have those gravitational moments, then you compare them to the ones measured by the Juno spacecraft or another spacecraft if it's not Jupiter. So when you do that, you're now able to make one interior model. And by the way, it's the way I'm doing it, but it's not the only way. Here, I assume the composition, get the density profile, and then calculate the gravitational moments. But one can directly look for the density profile that matches the gravitational moments, and those are called empirical models. And typically, here we have Beno and now Luca who are using this method in particular to study Uranus or Neptune. So now we can make one model of the interior of a giant planet, but of course, we want to study several of them in order to explore largely the parameter space. And so what I'm using is an MCMC in which I implemented my planetary calculation code. And so on the left-hand side, you see the 3 parameters of our MCMC calculations. So typically you have this core mass, the pressure at which the phase separation between hydrogen and helium occur, surface temperature, and so on. And here you can already see the effect of the equation of state, right? So the 3 different colors are 3 different equations of state. And you can already feel that depending on the equation of state that you use, you will infer different properties of the interior of the planet. And on the right-hand side, these are the data. So our MCMC is trying to sample models around the measured values of those gravitational moments, but also equatorial radius. And by doing so, we can study millions of models and fully explore the parameter space. So now I'm going to present you some results of interior models of Jupiter, which are based on this Juno data. And so I divided this section in 3 parts, 3 questions, let's say. And so the first questions that we wanted to assess is the envelope of Jupiter homogeneous or inhomogeneous? And by inhomogeneous, I mean that the mass fraction of heavy elements in the outer envelope is different from the one in the inner envelope. So here, I recall the structure of 2 types of models, 3-layer and dilute core models. And to answer this question, we studied both types of models. So the outer region of the 3-layer model is made of this molecular hydrogen helium pore layer. The inner envelope is made of this metallic hydrogen helium-rich layer. And then you have this dense compact core that is made purely of rocks and ices. And for the dilute core model, it's quite similar, but you add on top of that this 4th layer of a dilute core, where you have this gradual distribution of heavy elements from the very center towards the outer region of the planet. So in the case of the 3-layer model, we just wanted to look at the difference between the mass fraction of heavy elements in the outer region and the mass fraction of heavy elements in the inner envelope. So it's very simple. And so then we run our MCMC, again using 3 different equations of state. And for almost all of our models, we find this delta Z, which is equal to Z2 minus Z1, that has positive values. So this means that the envelope is inhomogeneous, sorry, and your inner envelope needs to be enriched compared to the outer envelope. Then we did the same exercise, but for the dilute core model. And in this case, we set Z1 equal to Z2, and we looked at the difference between Z dilute and Z1. And again, we found only positive values of this delta Z. So we could kind of quite robustly confirm that the envelope of Jupiter is inhomogeneous by looking at 2 different types of models, 3 different equations of state, and exploring the parameter space using this MCMC. And now if we look more in details at the distribution of heavy elements in those models, on this figure, I'm showing you the mass of heavy elements in the different regions of the models. And so the first thing to notice is that the total mass of heavy elements really depends on the equation of state that you choose. In the outer envelope of the planet, it seems that there is only a few Earth masses of heavy elements. So probably most of the heavy element mass is included in this inner envelope region. And quite independently of the equation of state, we found that the core mass is about 6 or 7 Earth masses. In the dilute core model, again, we see the influence of the equation of state on the total mass of heavy elements. And in this case, most of the heavy element mass is probably in this region of the dilute core. And so we found probably an upper limit on this compact core that cannot exceed 6 Earth masses. But many models tend to suggest that there is almost no compact core in those models. And then the second question that we try to answer is, well, if there's a dilute core inside Jupiter, how extended can it be? And so for that, I like to go back to this schematic that illustrates the distribution of heavy elements as a function of mass. And you see here this dilute core region with this gradual distribution of heavy elements. And I like to focus on one parameter that I call M dilute, which is nothing else than the extent of this dilute core in terms of mass. And so this M dilute parameter varies between 0 and 1 because it's in normalized mass. And so typically, if this parameter is equal to 0.5, that means that your dilute core extends to up to 50% of the mass of your planet. So again, we run the MCMC using different equations of state. And now we find a variety of solutions with more or less extended dilute cores. And if you remember at the beginning of the presentation, I told you that there were still some tensions between interior models and evolution models. So these are results from interior models, and previous interior models suggested quite extended dilute core. So they are shown here with those black stars. So we are able to confirm that we find similar results, but you can see that we also find a small subset of solution here where the dilute core is less extended. And on the other hand, there are some evolution calculations, and this is work by Simon and Ravit, where they model the long-term evolution of the planet and the mixing of the heavy elements over the whole evolution about from 0 to 4.5 gigayears. And so what they did is to look at two different scenarios. So in both cases, you have one primordial composition gradient or dilute core. So in the blue case, the dilute core at the initial state of the evolution doesn't extend more than 20% of the mass of the planet. And in the cream case, you can see that this composition gradient is much more extended. So they modeled the evolution of the planet, and at the end of the simulation, they find that in both cases, the dilute core region cannot extend up to 20% of Jupiter's mass, which is here. So while this result was quite in disagreement with those previous interior models, we are now able to find some interior models that are more in line with those evolution calculations. And then if we believe those interior models and those evolution calculations, well, it seems that the dilute core inside Jupiter extends up to 20% of Jupiter's mass. And if you do some simple math, 20% of about 300 Earth masses represents about 60 Earth masses. So the dilute core inside Jupiter should be confined in the inner 60 Earth masses of the planet. And what's interesting is that in Saturn, the presence of the dilute core has also been suggested. And inside Saturn, the dilute core should also represent a mass of about 50 to 60 Earth masses. So at that time, we concluded that we found a formation scenario that is consistent with both Jupiter and Saturn, where you form this dilute core by accreting both solids and hydrogen helium simultaneously when you force the inner 60 Earth masses that represent the dilute core. But then discussing with Ravit, then I realized that maybe we should not expect a same number for both planets, as of course both planets did not form at the same location and the surface density of solids is not similar. But still, I mean, we were able to find some interior models that were more in line with those evolution calculations. So I presented you the results of two papers, actually. So the first one suggested that the envelope inside Jupiter is inhomogeneous, and you really need an inner envelope that is enriched compared than the outer envelope. And the second paper, in the second paper, we are able to find interior models that are more in line with those evolution calculations. But of course, those models are very sophisticated, but they are not perfect, right? And a first limitation of those models is that they assume a surface temperature, which is actually a proxy for the whole deep interior. And so they assume a surface temperature that is quite warmer than expected, because Galileo measured 1 bar temperature of 166 K, and these are the values that our models suggest. And the second limitation of those models, and probably the most important one, is that they assume a metallicity in the outer region that is solar or slightly supersolar, while I told you at the beginning that we expect this Z1 value to be about 3 times solar. So it really seems that we have an issue in those models with the density in the outer region of the planet. And so that's why increasing the 1 bar temperature was one solution, because of course, if you increase the temperature, you can decrease the density. Something else that we try is to modify, let's say by hand, the equation of state, as it is an important source of uncertainty. but I acknowledge that it was not very conclusive. And so another possibility to decrease this density in the outer region is to simply decrease the heavy element content in the outer region of the planet. And this leads us to this hypothesis of an inverted Z gradient that I already mentioned at the beginning. So here you see again the distribution of heavy elements as a function of normalized mass. And this inverted Z gradient is illustrated by the model in black by Debras and Chabrier, where you see here a region, an outer region with very low content of heavy elements, and then this inverted Z gradient that may satisfy the Z value in the atmosphere of the planet. So here it's just to show you what we expect from the measurements in the atmosphere of the planet. And so in Jupiter, it should be enriched by a factor of between probably 2 and 4. So this idea of an inverted Z gradient is appealing because you can clearly decrease the density in this region and still match the measurements in the atmosphere here. But of course, then one has to justify it in the point of view of formation and evolution, because it seems a bit counterintuitive to have this inverted Z gradient. And so you have to make sure to be able to explain how you can form it and how you can maintain it over 4.5 gigayears. So I won't go into all the details, but we explored two scenarios to see if this hypothesis of an inverted Z gradient is plausible. The first one was to set this inverted Z gradient around the megabar level, and this corresponds to where this phase separation between hydrogen and helium occurs. And because you have an inner envelope that is enriched of helium, you can unfold for some more heavy elements on top and still make sure that it's stable. But the issue with this hypothesis is that the phase separation of hydrogen and helium actually occurs quite late in the evolution, so probably after 4 gigayears of evolution for Jupiter. So you would need to create a large amount of heavy elements very late in the evolution of the planet, and it's quite unlikely. So this scenario was ruled out. And then we studied a second scenario. And so this time, instead of setting this Z gradient at the megabar level, we put it at the kilobar level, so in an uppermost region. And this could exist due to the potential presence of a radiative zone. But of course, we don't have evidence that this radiative zone exists. But if it exists, this scenario might work because you would need less mass to accrete to enrich the envelope of the planets. But of course, you have still other issues, such as explaining that you can accrete the right type of heavy elements. So you need to be sure that the isotopic composition of what you accrete agrees with the isotopic composition of the atmosphere that we have measured. But this scenario might work, let's say. And so finally, I like to switch to evolution models of Jupiter and Saturn. And this is the work I've started to do since I arrived here in November. And I'll begin by showing you this figure, which illustrates the context of those evolution models for Jupiter and Saturn. So this figure shows you the effective temperature as a function of age, and the two black dots represent the measured effective temperatures of those planets, which correspond to the measured luminosities of the planets. And if one runs some basic homogeneous evolution models, and by homogeneous, I mean that the composition remains constant over time, well, this is what one will obtain with those black dashed lines. And you can see that there is a discrepancy between the predicted effective temperatures of those models with the ones measured So this indicates that Jupiter and Saturn seem to have an excess of luminosity compared to what we expect. And one potential explanation is that helium rain could be an additional source of energy. So I already told you about this helium rain, where you can deplete the upper region of the planet and enrich the inner region of the planet, and this can be an additional source of energy and can delay the cooling of the planet. And this is what you see here with those orange curves, which are now called inhomogeneous evolution models because the composition changes with time. And you can see that such evolution models that account for this process of helium rain can agree better with those with the measured luminosities of the planets. And so we'd like to know when helium rain start in Jupiter and Saturn, how it can shape the internal structure of the planet, and if Jupiter and Saturn are rather similar or rather different. And to do so, what we need to do is to couple those evolution models with a phase diagram of hydrogen and helium, which will tell us when this helium rain will start. But the thing is that the phase diagram of hydrogen and helium remains quite uncertain. And here, this figure shows 3 different existing phase diagrams with 3 different colors. So the red one is from an experiment, and the blue and orange ones are from numerical calculations. And so you see that you have a discrepancy of a few thousand K between those curves that predicts the demixing of hydrogen and helium. So what happens here is that typically a giant planet will start very hot, so probably around here, and it will cool down and eventually intersect with those phase curves. And if you look, for instance, at the orange curve, the intersecting region of Saturn, for instance, here, will be the region that undergoes this phase separation of hydrogen and helium. And this will lead to this formation of droplets of helium that will sink in the deep interior. And this can significantly affect the thermal evolution of your planet. So what I did next is to run those evolution calculations of both Jupiter and Saturn and couple those evolution calculations with those 3 existing phase diagrams. But because they are very uncertain, we allowed for some shift in temperature on those phase curves to see if we can constrain this phase diagram by studying the evolution of both Jupiter and Saturn. And first, I'm showing you the results for the evolution of Jupiter. So each column shows the results for one existing phase diagram. The top row is the distribution of helium today as a function of pressure, and the bottom row is the effective temperature as a function of age. So if you focus on the top left panel, so the black dashed line here is the results for an evolution models that is homogeneous. So the helium distribution remains constant because you don't account for this process of helium rain, and it is equal to the protosolar value, so about 27%. Then the first thing we did is to apply the original phase diagrams, and these are represented by the blue curves. And something I should mention is that the black dot here is the measurement of the helium content in Jupiter's atmosphere by Galileo. So ideally, one should reconcile the evolution of Jupiter with this measurement. But so if you use the original phase diagram, so the first one predicts probably too much helium rain because the outer region of the planet is too much depleted in helium. The second one predicts that helium rain hasn't started because the blue curve is constant. And the third case, with the experimental phase diagram is completely off because you see that after only 1.5 gigayear of evolution, the atmosphere of the planet is almost completely depleted in helium. So then we allowed for a shift in temperature of those phase diagrams to see if we can find solutions consistent with these measurements by Galileo. And here are the offsets in temperature that we need to apply in order to have an evolution model that is consistent with this evolution of Jupiter. So for instance, for this one, you need to apply a shift by about 1000 K, this one 300, and this one is very off because you need to shift it by about 4000 K. And something to notice is that actually the departure from the protosolar value is quite small, meaning that probably in the outer region of the planet, you have 23% in mass of helium, and in the inner envelope you have 28%, which is not far from 27%. And you'll see that for Saturn, it's much more dramatic. For Saturn, we don't have such a measurement of the helium content in the atmosphere. No consensus has been reached yet, and we didn't have a probe like Galileo for Jupiter. So what we did is to apply the constrained phase diagram by with this offset in temperature, and you apply that to the evolution of Saturn. And here are the results that we get. And so while for Jupiter, the departure from this protosolar value was quite small, here you see a huge helium gradient. So in the outer region of the planet, instead of 23% for Jupiter, you're probably at 15 or 10% in mass of helium. And then you have this huge helium gradient that covers a significant portion of the planet. And you even have a region where the mass fraction of helium is equal to 1. And we call this region a helium ocean or helium core because it's purely made of helium. So this means that you have so much helium rain that the droplets sink and accumulate above this potential pure heavy element core, and you progressively form this helium ocean. So on the one hand, we have only slight demixing for Jupiter, but for Saturn, the picture is really different, and the planet is much more affected by helium rain. And this is simply due to the fact that the planet is colder. So helium phase separation starts earlier in the planet. And so in Saturn, you have this large helium gradient, this helium ocean, and we are now able to estimate the atmospheric helium content in Saturn. And so such work that I did with Simon and Ravit was submitted to a paper a few weeks ago. And so to conclude, well, my last slide summarizes more or less what I presented today. What I wanted to mention also, because I didn't have time to present it, is that I'm also working on exoplanets. And this work on Jupiter, the equation of state, has direct consequences on exoplanets. And well, I think the purpose of this presentation was also to tell you about what I've been working on and what I'm working on now. But more importantly, I'm in the same office as Pedro, so please, I would be happy to discuss if you want.
So this helium ocean for Saturn,
Mm-hmm.
of course, in its favor, there's no deluge core.
Yeah.
So what is your, how do you think this would look if you do have this, which is quite extended?
In the evolution?
Yeah, because then you can't really have helium. Because there's already all of these heavy elements, so you can't have super high helium.
Yeah, so in what I presented, of course, yeah, there is no dilute core of heavy elements in those evolution models. There was only a pure heavy element core, so that's why the helium was stacking above this. But if you had a gradient of Z, I think if you start helium rain first, you will, accumulate a small amount of helium in the deep interior and progressively have more helium stacking above the dilute core. So I think there will be less chances of having this dilute core. But if you have enough helium rain sinking maybe on top of this dilute core, you could have this helium core. But of course, it depends then on the extent of the dilute core.
Do we have an idea of how a mixture of heavy elements and helium behaves?
Well, I think there was some initial calculations from Militzer where they added heavy elements in mixtures of hydrogen and helium, but usually they don't have more than 10% of heavy elements.
Just helium.
And heavy elements, yeah, I don't know. I mean, one would have to run those calculations.
So I'm wondering about the effect of the moons of Jupiter on this very precise
Mhm.
measurements of the inner flow. So I guess like the direct effect is probably taken into account. But wouldn't you also expect like neutral moments to appear because of tides? And is it obvious that they are so small that we don't count them?
Yeah, so in the measurement of those gravitational moments, I mean, the instrument people during the measurements of those gravitational moments, they have a very sophisticated model to relate those gravitational moments to the perturbation in velocity that we see on the spacecraft. And I think the accuracy is really small, like it's, I think centimeters per second. And of course, this model accounts for the influence of the gravity from the gravity of those moons. But then in the interior models I presented, we don't account for tides. It may have an effect, but I think it would be small. But yeah, I don't know. There we have measurements, for instance, of the love numbers that may be used to constrain the interior. But in what I'm doing, I didn't use them, but I know that there are work. There is some work using these love numbers, and they could be used to constrain the extent of the dilute core. But so far, I mean, you can't really determine if it will be more or less extended. Yeah.
So you said the emergency gradient might be in kilobar range.
Yeah.
And does it line up with the helium ray? I think whatsoever.
No, helium rain would be probably at the megabar level. So it will be in an upper region.
So what makes the emergency gradient stable?
So in this case, you would have a radiative region. And so in this radiative region, you have a temperature gradient that is smaller than the adiabatic one. So what's below this stable region would be, let's say, colder. Colder means denser. So you can afford some more heavy elements if you make the thing below a bit denser.
And they won't sink down at first.
Well, then it's another question. If over the 4.5 gigayears evolution, you wouldn't have, like, for instance, diffusion through this stable region. And a quick estimates would tell you that after a few million years, you should expect some diffusion through this stable region. But I don't know, the evolution calculations from Simon suggest that you may be able to have a stable region maintained over the whole evolution. But it's a complicated scenario. But so far we haven't found something else to explain the enrichment of Jupiter's atmosphere, because those interior models, really, if you try 2 times solar, you can't find any solutions that fit the gravity data. So that's why we're coming up with those complicated scenarios.
So like an equation of state for helium hydrogen mixture, I'm not so sure it will constrain precisely where is this helium rain starts, because well, like in general the equation of state is computed over a very coarse grain grid, so you can really constrain the point where it starts. So I was wondering if do you think it's more effective or important to have an equation of state for the mixture, or to constrain where is the hydrogen?
Well, personally, I think I would prefer an equation of state of hydrogen and helium, because so far we have mostly relied on the work of Militzer, and it's probably the only very extensive equation of state we have for a mixture. While for the phase separation, the phase diagrams, we have several of them, and it's very uncertain. So yeah, I think I would prefer that you do an equation of state of the mixture.
So I think they are equally important. Focus on if you do structure modeling, and then you really want to understand, the distribution of elements in Jupiter, you can say, okay, I want the hydrogen, and I really care about the, percent different density. But if you try to understand the evolution and luminosity, then actually you know more about this expression.
Yeah. Yeah, Henrik, you can ask your question.
Okay, thank you very much. Can you hear me?
Yeah.
Okay, perfect. Thanks for the nice talks. I was wondering, when you make these interior structure models and you always split, I mean, I would do the same, right? But we always split this into X, Y, and Z. And I was wondering what you think might be the way forward with regards to the heavies, because I kind of feel like rock would be very different from ice, which might be very different from some kind of iron or whatever. So I wonder if we use different compositions for the core, if we get completely different or slightly different interior structures. I was wondering on your opinion about that.
Yeah, so I mean, I think in the case of Jupiter, the core is quite small. You see, in the 3-layer models, it wouldn't exceed 6 Earth masses. So if you have 6 Earth masses of rocks, ices, it wouldn't influence that much your gravity data, especially because the gravity data is very sensitive to the outer part of the planet. So I think in a planet like Jupiter, having a core made of rocks or ices wouldn't change that much. But maybe in other planets like Uranus, Neptune, it would have an important effect. Then, yeah, in my models, the Z value is actually a Z ices plus a Z rocks. So I'm using an equation of state for water and one for rocks. But I think so far we can't really disentangle what should be the amount of ices, what should be the amount of rocks, because I think because the planet is mostly dominated by hydrogen and helium, the influence of the equation of state of these elements is much more important.
Okay, and your estimate of, let's say, 6 Earth masses for the core would also not change if you use a different material for that or a different equation of state.
Probably it would change very slightly. Of course, if it's rocks, it would be slightly smaller than ices, but I wouldn't expect a factor of 2 or 3 difference.
Okay, thank you.
Okay, further questions? Then let's thank Saburo again. And have a great semester break. And